PreAP, PreCalculus, Notes 4.2, Finding the Rational Roots of Polynomial Functions. Really what this section is all about is the rational root theorem. Going to come at you sideways here a little bit. You writing all this down maybe not be that important what I'm going to put in here. In hindsight, I wish I would have just included it in your notes already. Consider the quadratic function, this little fella right here. We know it has a degree of 2, so there are 2 roots. In the left-hand box below, list all possible pairs of factors that could be factors of the function. Now that's kind of a lie when we say all the possible factors. Here's how these were formed. We formed these in a way so that if you multiplied the first 2 terms together, you would get 3x squared. And if you multiplied the last 2 terms together, you would get -6. This completely disregards the 17x. Now the reason we disregarded the 17x, if we knew how to factor this so that happened, this would be easy and be finished. There's no point in doing any of this. We're trying to make a point, and the point is that if you list all the combinations of factors that give you the correct first term and last term, and disregard the middle term, there is a way that you could list all these factors. So we have these combinations here like 3x plus 1 and x minus 2, which means the possible roots of this, according to the factor theorem, would be -1/3 and a +6. So we've listed here all the possible roots of f of x based upon the leading term and the constant. From the equation of f of x, what are all the factors of the constant term? Well, the constant term was 6. So what are factors of 6? Plus or minus 1 goes with plus or minus 6. 1 times 6 is 6. -1 times -6 is +6. Plus or minus 2. Plus or minus 3. 2 times 3 is 6. -2 times -3 is 6. Those are all the factors of the constant term. What are the factors of the leading coefficient? The leading coefficient is 3. Its factors are plus or minus 1 and plus or minus 3. Now, if we place each factor of the constant term, that's this one, over each factor of the leading coefficient, that's these ones, that's going to give us a list of all the possible roots. So, in summary, if we were to write plus 1, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, over top of plus or minus 1 and plus or minus 3. This would give us combinations. If we take 1 divided by 1, 2 divided by 1, 3 divided by 1, 6 divided by 1, we get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Now if we take each of these and divide, if we take each of these and divide them by 3, we're going to get plus or minus 1/3, plus or minus 2/3, plus or minus 3/3, which I'll talk about in a second, plus or minus 6/3, which I also talk about in a second. We don't need to list this one because we've already listed it here. 3 divided by 3 is 1. We don't need to list this one because it's already listed right here because 6 divided by 3 is 2. So we end up with 1, 2, 3, 4, 5, 6 possible roots of f of x based upon the factors. Now if you compare this list with the list that's up here, you will find that they're the same. Yes, this lists more than 6 things, but there are positive and negative versions, and some of these things are repeated. So we got 1, 2, 3, 4, 5, 6, 7, 8 combinations, but there is no number that's up here that's not included down here. So what does that lead us to? Well, we'll get there in a moment. We're almost at what it's leading us to. Now consider the function that we've just, now it's a new function, function f. Estimate the roots of the function. Well, kind of difficult. Clearly, this one is -3. So we're going to say roots that are likely. -3 is a root. These ones here aren't integers. So I'm guessing this one might be -2/3. Maybe. I don't know. This one here looks like it could be halfway between. Maybe that's 1/2. Notice I wrote the word likely, the likely roots. Well, the rational root theorem is going to help us avoid doing all of this and going directly to this. The rational root theorem. A list of all the rational numbers that are possible roots of a polynomial function can be formed by placing each integer factor of the constant term over each integer factor of the leading coefficient. In Algebra 2, you might have called it P's and Q's. Where P is the coefficients of the leading term and Q's are the constants, and you take your Q's and divide them by your P's. So here's how we're going to do this work. Apply the rational root theorem to list all the possible values that could be for this function. So we're going to say the possible rational roots. We're going to take factors of the constant and divide it by factors of the leading coefficient. The factors of the constant are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. The factors of 6 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Now, to get all the possible combinations, and I'm not going to do this again. I'm going to do this time, and then you can decide if you need to do this next part. Take each of these and divide them by 1. We take each of these and divide them by 2. We take each of these and divide them by 3. We take each of these and divide them by 6. Or we can just leave it like this. In the future, I'm going to leave it like this. So if we divide each of the top numbers by 1, we get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. If we divide them each by 2, avoiding repeats, we got 1 divided by 2, which is a half. 2 divided by 2 is 1, I already have it. 3 divided by 2, 6 divided by 2 is 3, we already have it. Now I'm going to take each of the top numbers and divide them by 3. Got plus or minus a third, plus or minus 2/3. 3 divided by 3 is 1, we already have it. 6 divided by 3 is 2, we already have it. Now we're going to divide each of the top numbers by 6 and get plus or minus 1/6. Plus or minus 2/6 is the same as 1/3, don't need it. Plus or minus 3/6 is the same as 1/2, don't need it. Plus or minus 6 is the same as 1, we don't need it. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, doubled because it's plus or minus. There are 18 possible rational roots. From the list above, eliminate those values that do not appear to be the values indicated on the graph. Which values of the list do not appear to be roots? All right, so this is the graph we were talking about. We thought maybe it was something like this. Now, if we look down here at our list, clearly it's crossing at -3. There's no roots to the left of -3. There are no roots to the right of 1. So as far as eliminating goes, we can eliminate plus or minus 2. We can eliminate positive 3, but not -3. We can eliminate plus or minus 6. There's no root between 2 and 3 negative. So like -1.5, positive 1.5 doesn't make any sense. So we can continue to eliminate things, or we can just say, which ones do we think are highly possible? Looking at our list, are, I'll tell you what, I'm gonna bring this graph down here so I can see this better. There we go, now we can see it. So of these possible rational roots, we're going to abbreviate possible rational roots. We're going to make a list of highly possible rational roots. Definitely -3. Be shocked if it wasn't. We need a number between 0 and -1 that looks like it's closer to -1 than 0, like maybe a -2/3. So -2/3 fits in this. Could be -1/2, depending on how our graph looks. Don't think it could be -1/3. I'm going to go with -2/3. Maybe we're right. Maybe we're wrong. We're going to figure that out in a moment. We need a root between 0 and 1. That would be a half. Looks like it could be very likely a half. Doesn't look like it would be a third. Doesn't look like it's 2/3. Doesn't look like it's a sixth. I'm pretty confident it's a half. Now, it might not be a half. It's possible that it's none of these, because these could be irrational roots. The rational root theorem helps you find irrational roots. What can be done to verify that these are in fact roots of the function? Well, we could use synthetic division. If -3 is a root, we can divide that into our polynomial, which had coefficients of 6, 19, 1, and -6. If we do synthetic division, we have confirmed that -3 is a root. That is wonderful. Now we could then synthetically divide this by -2/3 and or 1/2 to see if they work as well. There'd be nothing wrong with that. But I would rather not do that. I'd rather take the depressed polynomial and see if I can factor it. This particular one is not easy to factor, but if I split the middle term, which I'll explain how I did that in a second, this middle term of x, I made a plus 4x and a minus 3x. How I chose that was I multiplied 6x squared times -2. I need two things that multiply to get -12x squared. If you multiply these, you get -12x squared. And those same two terms add to be a positive 1x. These add to be a positive 1x. If we group together these and these, we're going to get the GCF of each group. We're going to get 2x times the sum of 3x and 2. GCF of the next group is a -1, leaving us with 3x plus 2. So this factors into a 3x plus 2 and a 2x minus 1. Guess what? This root would be a -2/3. Boom. This root would be a positive 1/2. Boom. So the roots for this, we know for certain now, are -3, -2/3, and positive 1/2. Now I intentionally factored this problem once I got to this point to see if I could get this. However, in hindsight, it would have been faster to not factor it, but to synthetically divide this by -2/3 or a half. A half would probably be the easiest. All right, let's do two more examples. Use the rational root theorem to determine the rational roots for each of the function below. Use synthetic division to verify that they are in fact roots. So I'm going to first list the possible rational roots. I'm going to take factors of the constant and divide it by factors of the leading coefficient. That's plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. I'm not going to list all the combinations of those. This gives me enough to go by to list, because what I'm really after is the highly possible rational roots. 2, highly possible. This looks like it could be negative 2.5 or negative 5 over 2. That seems very likely. This one here is less than a half. So what choices do I have for less than a half? I have a third and I have a sixth. This looks more like a third of the way than the sixth. So I'm going to say a third. Now, these could all be right. We could have some combination of these right and some combination of these that are not. Let's check this out. Synthetic division. Take my coefficients. Now what do I want to choose first? I want to choose the easiest one, which 2 is the easiest for me to do. Bring the first term down, multiply 2 times 6, add, multiply 2 times 13, add, multiply 2 times negative 5. So that checks out. Now instead of trying to divide this and split the middle term, I'll see if I can divide this now by a third. See if this gets too crazy. If it does, I'll just retract and divide again. Bring the 6 down. 6 times a third is 2. 13 plus 2 is 15. 1/3 of 15 is 5. Well, that worked out. Let's see if we can divide this by negative 5. Well, let's not. At a certain point, negative 5 halves, that seems pretty difficult. So I'm going to take this depressed polynomial, 6x plus 15, set it equal to 0, and see if I get negative 5 halves. That reduces. I can divide the top and bottom by 3 and get negative 5 halves. So we've just confirmed that each of these work. So the roots, negative 5 halves, 1/3, and 2. You definitely want to start this process with synthetic division. This has got to be done. From there, you can take the depressed polynomial and you can factor it, set it equal to 0 and solve it, or you can continue to try your highly possible roots. All right, number 18, possible rational roots. I need factors of 3. I'm going to divide those by factors of 18. Plus or minus 1, plus or minus 3. Factors of 18, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18. Not great, but there's so many fractions involved in this. So let's look at our graph and see if we can figure out. This one here looks like it might be halfway between negative 1 and negative 2. So I'm going to say a highly possible rational root would be negative 3 over 2. Is that one of my choices? Sure. Whoops, right here. Negative 3 over 2. Between 0 and 1, I wouldn't say that's half. Maybe that's a third. Is a third an option? It is. I'm going to go and say maybe it's a third. Now, whatever this one is, it's going to have an even multiplicity because it's tangent. So I'm saying a third is going to happen 2 times possibly. So let's do some synthetic division. I'm going to take 18, 15, negative 16, and 3 and divide it by a third. Third seems easier than 3 halves. A third of 18 is 6. I add a third of 21 is 7. I add a third of negative 9 is negative 3. That works. Now, since a third worked once, a third has to work twice because it's an even multiplicity. So let's divide it by a third again. Bring the 18 down. A third of 18 is 6. 21 plus 6 is 27. A third of 27 is 9. Hey, we got a remainder of 0 again. No shock, that worked twice. Now I'm going to take the depressed polynomial, 18x plus 27, set it equal to 0. Get x by itself. Handwriting is steadily getting worse. And that's saying something because it's always been bad. We can divide both 27 and 18 by 9 and get negative 3 halves, which confirms that one as well. So the roots for this little fella are negative 3 halves, 1 third, and 1 third. And more specifically, these are the rational roots. Now we found all the roots, but it's possible that we could just find some of the roots and we are missing the irrational ones, or we're missing the imaginary ones. All right, that concludes the notes. To sum up, we can use the rational root theorem to make a list of possible rational roots. Then from there, look at the graph to try to narrow it down to highly possible rational roots. Then we can use synthetic division to test each of these highly possible things, see if we get a remainder of 0, and if we do, it is in fact a root. Please do the homework for 4.2.